Hello, and thank you for taking the time to listen to our presentation. We are Group 6, and today we will be recommending a methodology for analyzing Caterpillar's dealer structure. We will be using the data provided in the case and reviewing 3 different network structures throughout our presentation.
Our team consists of 5 members: Liam, Jake, Andrew, Elisa, and Caroline. Here we have an overall summary of our work. Our goal was to create a standard methodology that considers all components necessary to effectively approach a network redesign analysis. Caterpillar has the opportunity to eliminate inefficient expenses and use of resources to achieve higher overall service levels to their dealers. We focused our methodology around these objectives and are excited to present an adaptive Excel model that can handle the redesign decisions given any dealer network scenario. Our model assesses dealer demand, lead time and safety stock, holding and ordering costs, and target service level in order to make an overall recommendation.
In order to choose the best network structure, we had to understand the benefits and drawbacks of each design, which included the single-tier, multi-tier, and hybrid model. The single-tier model provides clear forecasting and level inventory. However, there is no differentiation in how high and low the turnover deals are sourced, which can lead to lower levels of customer service. The multi-tier model, on the other hand, contributes an extra layer of protection for dealers with safety stock and increases service level. A drawback of this model, however, is centered around dealers ordering less frequently and disrupting the demand and transportation distribution for CAT. Finally, our group analyzed the hybrid model. For our findings, this was the most adaptive model as it would accommodate to the evolving demand of dealers, but it needs for a clear methodology to outline how it is set up is a challenge for some businesses. For this slide, we were given data on a multitude of different parts and demand orders from 17 dealers. Using the information, we were able to calculate different findings using the 3 costs: safety stock, ordering, and holding cost. We used this as part of our methodology for making a recommendation.
Our model begins by calculating the safety stock cost by a risk pooling approach. Risk pooling was our first inclination because it directly relates to the decision of a central warehouse. It allowed us to calculate the level and cost of safety stock in a flat versus a hub and spoke structure. Pooling safety stock in a central distribution center is often more beneficial because it reduces the overall level of risk in the supply chain. Using the data provided to us, we found that the safety stock cost was almost 3.5 times less in a hub and spoke model. This model significantly reduced the amount of safety stock that was necessary at each of the dealers by pooling it in a central warehouse. However, we also found that safety stock costs were never more than 20% of the overall cost of the model. It is important to keep other factors in mind when making a supply chain network decision. Ordering costs were the second step in our model, and they made up the largest portion of the total costs for both structures. Based on the data in the case, we modeled the ordering and related costs for each structure. The hub and spoke model benefits by consolidating all orders from dealers into large quantities that can be placed with the Caterpillar distribution center. However, the hub and spoke model also has a higher overall logistics cost for each part at $1.80 per line compared to the flat structure's $1 cross-dock per line. Due to the higher cost per line for the hub and spoke structure, the overall ordering and associated logistics costs were significantly higher than for the flat structure. The difference was almost completely attributed to the associated logistics cost. There were over 270,000 lines in the customer demand, and the associated logistics costs were multiplied by each of those lines. These were then added to the related ordering costs for each structure. The ordering costs were not significantly reduced by the consolidation of orders with the hub and spoke structure, based on our assumption and of a 50% reduction in number of orders.
Our team calculated the various holding costs for each structure and found that the single-tier structure was the most cost-effective, costing approximately $72,000 less than the multi-tier model. There is high holding cost for the multi-tier structure primarily because the hub must aggregate all of the demand from the dealers. Our team used the previous 3 calculated costs to build an adaptable Excel model that Caterpillar can use for any dealer network scenario. After inputting the given data into the model, we found that the single-tier structure was the most cost-effective overall, considering the demand distribution, ordering costs, holding costs, safety stock, and target service levels. Here, you can see our comprehensive decision framework, including costs, geographic location, and impacts on the current supply chain. Even though our team found the single-tier structure to be the most cost-effective model in this scenario, there are many other important factors that need to be considered in order to select the most optimal model. We believe that if transportation costs, which often make up a massive percentage of total costs, were considered, a multi-tier structure may have been the superior option. Also, geography and proximity of the warehouses are extremely important in determining the feasibility of a multi-tiered structure. Our team recommends that CAT uses a more comprehensive set of data, including transportation costs and geography data, when making these decisions to ensure accuracy of final cost and feasibility. Dealer network redesign can cause both positive and negative ripple effects for Caterpillar's own parts network depending on the change being made. A redesign of any type will disrupt transportation routes and cause for a readjustment period before efficiencies are realized. Additionally, a consolidation redesign, such as moving from flat to hub and spoke, will change dealer expectations on lead times and likely contribute to dealers ordering in larger quantities from the hub. This will negatively impact the demand distribution put on Caterpillar's distribution centers. The graphic on the right is meant to emphasize how demand distribution could lead to a bullwhip effect inefficiency as the amount of extra inventory will increase from the dealer warehouses to the Caterpillar distribution centers. However, the positive ripple effects would outweigh the negatives when an optimal redesign is selected using our methodology. These positives begin with increasing service levels to dealers and reducing supply chain costs, which allows Caterpillar to grow revenues, open more dealer locations, and ultimately expand the business in an efficient and organized manner. Once redesigns are handled through a set methodology, they will be easier to forecast, and the accuracy of Caterpillar's demand forecasting and inventory management will improve across the business and save vast amounts due to the breadth of Caterpillar's supply chain. To close, our framework provides a transformative change for the way in which Caterpillar approaches dealer network redesigns. Currently, Caterpillar's dealer network is evolving with no standard method on how to adapt to growth and evolving dealer demands. Our model addresses all facets of inventory costs, geographic location, and the impact changes have on the current supply chain. Furthermore, our framework provides a data-driven approach to offer a clear pathway for Caterpillar to optimize their decision-making in future redesign scenarios and leave current inefficiencies as a thing of the past. Thank you for taking the time to evaluate our presentation. Please reference our appendix and Excel model for context on any questions you may have. Have a great day.